Mmm, that's some good H2O. Hello. I want to talk to you guys today about air masses and how they're related to humidity. Something that you are familiar with. You all felt humidity, you've experienced it before, and now it's time to kind of learn a lot more about it, and what it is, and why it is the way it is. It kind of all starts with how Earth is heated. We know Earth is heated unevenly, right? So here's Earth out in space. My bald head is the sun spitting out, you know, radiation towards the planet like this. And it hits the planet most directly near the equator, right? And we know that because it hits the planet more directly at the equator, that down here is where the warmer surfaces are. Up here, where it gets the indirect hit, it's the colder temperatures. But we also have to take into consideration that there's two major types of land surfaces. There's, well, two types of surfaces. There's the land surfaces, and then there's the water surfaces. Now, being a water surface means that you're going to contribute a lot of water vapor into the atmosphere. Way more than if you're a land surface, because you don't have as much exposed liquid H2O to evaporate. So you look down here near the equator, because it's warm water, it releases a tremendous amount of water vapor into the air. Up here, closer to the poles, the water still does get water vapor into the atmosphere, just not as much because the water doesn't have as much thermal energy to complete more evaporation, because it's colder water, because it's getting that indirect hit from the sun. Okay? So it creates these air masses that move around the planet, right? So here we are sitting in New Jersey. That's us. Say hi. If this air mass containing warm air that's filled with water vapor comes from this hot tropical water and it moves into New Jersey in the summertime, it's a pretty lousy day. It's like 90 plus degrees and super humid and it's disgusting. That's a day you're inside with the air conditioning. You don't set foot outside. Now, summer months still, if this dry, cool air comes to visit us in New Jersey, okay, that's the kind of day when it's like 78 degrees, 82 degrees, perfect blue skies, no humidity, and that's the day where you're like, yes, it's awesome. So, what we're going to talk about though is feeling the water vapor that's in the air compared to feeling the dry air. All right? When we talk about that, we're talking about humidity. Humidity is a measure of how much water vapor is actually in the air. So we take a look at some low pressure warm air, okay? Now, if you look at this low pressure warm air, these two containers have the same amount of air particles, and they're spread out the exact same amount. But if you look, there's the water vapor particles. In this air, there's a lot more water vapor particles, which means that these are both tropical air masses, except that this one is a tropical air mass that's over water, okay? It's maritime, so it has a lot more water vapor in it. This would feel much more humid than this would. Humidity can exist in colder air too, like I showed you on the globe. Okay, here we have some polar air masses filled with cooler air. Cooler air makes higher pressure, right? So there's not as much room in between the particles in high pressure air, so it can't get filled with that much. It can't get filled with that much water vapor. So when we look at these two, you have water vapor here and less water vapor here. Not that much room for the water vapor, so it can't feel as humid. All right? But what I want to do is I want to talk to you about this is more humid than this. This is probably maritime, this is probably continental, right? Let's look at our two maritime air masses of hot and cold air. Okay? These are both maritime. How do I know? Because they're filled with lots of water vapor. But what you'll notice is there's a different, what we call relative humidity. Relative humidity is, well, out of the open space that's available for water vapor, how much of it is actually filled up with water vapor. Okay? So these have a different relative humidity. How do we measure relative humidity? We use a tool like this. A psychrometer. It's a great word to say. Try it with me. Psychrometer. Thank you. Well done. What a psychrometer is, it takes two thermometers. A dry thermometer with the dry bulb right here, that's the bulb, okay? Look at me. And then you have the wet bulb thermometer. This is just a paper towel I taped onto this thermometer. What I'm going to do is, to make it a true wet bulb, I'm going to go wet it in the sink. The sink's very far away. Okay. In this psychrometer, we have the wet bulb and the dry bulb. The dry bulb right now is measuring the temperature of the air in my kitchen, which is approximately 22 degrees Celsius. So the air in this room is 22 degrees Celsius. The wet bulb here is a different story altogether. Okay? Before I wet this cloth, it was 22 degrees Celsius. But you see, water is leaving this wet paper towel. We know that if we leave a wet paper towel out, it'll dry eventually. Why? Because evaporation takes place and the water particles leave the paper towel. That's happening right now. When evaporation occurs, it requires energy. What kind of energy? Thermal. So when the water molecules jump off this paper towel and into the air, they take thermal energy along with it. Now, if you take thermal energy away from something, what happens to its temperature? It goes down, right? So this thermometer, because evaporation is happening off of the wet bulb, this thermometer is starting to record lower temperatures. All right, so let's give it a minute here to finish adjusting. I'll do a time lapse for you while we're waiting. Okay, just kidding, I don't have time lapse. Okay, kind of like when you run around outside, okay, and you're doing exercise. Your body has a cooling down mechanism built into it. Sweat, okay? If you're feeling hot, you sweat. Why? Because your body's smart and it's like, whoa, hey, our body temp's too high. Gotta lower it. How do we lower it? We put moisture, we put liquid on the outside of our skin so that way it evaporates and takes thermal energy with it, thus cooling you off. All right, so my wet bulb thermometer is about 18 degrees Celsius. Okay, 22 on the dry bulb, 18 on the wet bulb. So, what does that 4 degrees Celsius difference mean? Well, the bigger the difference between the dry bulb and the wet bulb, the more evaporation. Why would more evaporation happen? Because there's more room in the air for water vapor to go. If the air in this room was filled with water vapor, making it feel humid in my house, then there would be no room for water to jump off this paper towel. But my house is pretty not humid, so there's lots of open space. So lots of water vapor is leaving, making the temperature drop, drop, drop. Yeah, it's holding steady at 18. So we have this chart, okay? And what this chart does is it compares the two thermometers. Compare. This column right here tells you the temperature of the dry bulb. Now, in my house, the dry bulb said, what was it? 22, okay? So I'm going to update my chart to show you where 22 degrees is on the dry bulb. So 22 degrees on the dry bulb is everything in this horizontal row right here. These numbers that are across this part of the chart are numbers that are the difference between the dry bulb and the wet bulb. 22 and 18 degrees difference, the difference between 22 and 18 degrees is 4 degrees. 0, 1, 2, 3, 4. So I'm going to highlight this column to indicate that this is our difference between the dry bulb and the wet bulb. Okay? Now, notice the point of intersection. Okay? The point of intersection says 68. What does that number mean? Well, that number is a percentage. It's called the relative humidity. That means that out of all of the available space in this room, in this air, for water vapor to fill in, it's already filled in with 68% of its open space is already filled in. Okay? If that means that the air in this room is spread out, leaving room for water vapor. Out of all that available room, 68% of it is already filled. If less than 68% of it was already filled, this water would jump off and cool the wet bulb a lot faster. Okay? And there would be a bigger gap between temperatures. But it can't cool any faster than this because 68% of the air is already filled up with water vapor naturally. So there's not that much room for any more additional water vapor. I guess my house is a little more humid than I thought. It's a pretty gross day outside. It's muggy. My air conditioning nor heat is actually turned on right now, so it's probably just getting some of the outside air mixed in, which is why it's probably 68% humid, relative humidity. Okay, so thanks for watching, and if you have any questions, ask. All right, guys? Cool. Thanks.